So let us continue. Few more questions which are related with the functions implementation by using these NAND gates and NOR gates. So note down. Identify the minimum number of two input NAND gates required identify the minimum number of two input NAND gates required to realize two input exclusive OR gate. To realize two input exclusive OR gate. It is one of the standard question. It was the question couple of times in the GATE exam. Recent times it was the question 2016, I think, in the GATE exam. It was the question, very frequent question. No need to talk which year. Couple of times it was the question. It's a standard question. Suppose consider we are having options here as, say, these are the options. Let us consider. The answer is supposed to be this 4. If you look how it is so, the question what we are looking is, we want to implement this exclusive OR operation by using minimum number of two input NAND gates. By using these universal logic gates, NAND gates, we want to implement, and the gate count is supposed to be minimum. This A exclusive OR operation as a POS form, if I read, the POS expression is A complement or B complement and with A or B. By using De Morgan's property, possible to read the first sum term as AB whole complement. So AB whole complement and with A or B. Let's consider AB complement as, say, M. Then we are looking, this is MA or with MB. We started the expression with SOP form, and the mathematical or Boolean algebra properties manipulation, we are looking this, we started the expression with the POS form. With this properties usage, we are looking this in the SOP form. We are reading, or we manipulated to SOP form with the intermediate term M. Now, with the knowledge what we learned while working one of the previous example, once it is SOP expression, we are having possibility to implement by using two-level 9-9 circuit. As it is this expression, we can implement with a two-level 9-9 circuit. At level 1, 2 NAND gates because of two product terms. And of course, at level 2, only one NAND gate. So this is A input, this is B input, and we need second input to each gate is M. Then No need to mention, similar to the previous one of the previous question, you must accept this is Y, that is A exclusive or B. If you want clarity, we must speak as now MA complement. Here it is MB complement. So this gate output MA complement and with MB complement, whole complement. This will be MA or with MB. Now look to the M. M is AB whole complement. It means for reading M, we are in need of one more 9. We are in need of one more 9. Hence, it is the one what we are looking as M. So while counting this total number of gates, we are looking as 4, and the readout for this circuit is basically A exclusive or B. Hence, we are looking here to realize this 2 input exclusive OR gate, the minimum number of 2 input NAND gates we need as 4. So to speak the answer to this, no need to by heart anything. It is a way of it is a way of learning. So with the conceptually, if you are looking, this A exclusive or B operation we are reading as a POS form. Later, while defining an intermediate term M, we are converting that POS to SOP. Once it is SOP, it is standard 2-level 9-9 circuit. With that knowledge, without by hearting anything, we are able to speak the answer to this question is 4. Or this is a logic circuit for this question. Suppose we are taking the same question, say on the exclusive NOR operation. Instead of XOR, suppose the same question we are taking on the exclusive NOR. For reading exclusive NOR operation, possible to speak now, we need one more 9. This 9 gate output, suppose if I speak as F supposed to be Y complement, where Y complement is A exclusive or B complement, nothing but A exclusive nor B. It is nothing but A exclusive nor B. So this is to work as a inverter. It is work as a inverter. Hence, for realizing exclusive NOR operation, we need 5 gates. Here we need 5 gates. Here we need 4 gates. 5 90 gates. 2 input 90 gates. Here 4 2 input 90 gates. So just by using universal logic gate 9, we are having implementation of this 9 as well as we are implementation of this XOR as well as exclusive NOR, just by using only 2 input 9 gate, that is universal logic gate. We are having implementation of exclusive OR gate as well as exclusive NOR gate. The same thing we are supposed to try even for exclusive NOR. So let us take the question here as identify the minimum number of 2 input NOR gates required to realize 2 input exclusive NOR gate. Suppose the options we are looking here as like this. While looking in a smart way, इसका आंसर ऑप्शन बी दे सकते. We can look to the answer with the knowledge of exclusive OR without talking anything. The smart way, if you think the answer is supposed to be 4. Let's look how we are having this is answer as a 4. The XNOR operation on A and B possible to read in the SOP form as SOP form. It is A complement B complement AB. Let define M as A complement B complement. It is nothing but A or B complement. Let's define M as A complement B complement. It is nothing but A or B whole complement. It is A or B whole complement. Now, let us substitute this A complement B complement as a M. So, M R with AB. By using distributivity, possible to read this as M R with A and with M R with B. So, what we are looking, we started our work with the SOP and we are reading with the manipulation while using the intermediate term M. While using the intermediate term M, we are reading this as a POS. Once it is a POS expression based on our one of the previous question knowledge, possible for us to speak this POS expression we can implement by using two-level NOR circuit. If you develop the two-level NOR circuit for this, the two-level NOR circuit we are reading as so at level 1, 2 NOR gates because of two sum terms. At level 2, of course, only one NOR gate. The inputs, if you look, A, here B, and for both these gates, one common input, that common input is M. That common input is M. It's a two-level NOR circuit without any verification possible for us to speak this must be now Y. For clarity, let us verify this is MR with A complement. This is MRB complement. So we are having the second level NOR gate output. Second level NOR gate output is MR with A complement or with MRB complement whole complement. So using De Morgan's property, it is resulting as MRA and with MRB. It's a POS what we mentioned. Of course, it is nothing but equal to Y. It is nothing but equal to A exclusive NOR B. Coming to this M we are having possibility to implement by using a NOR gate because M is A or B whole complement. So for implementation of this M, we need a NOR gate. So one input is this A, other input is B. So based on this, while counting these gates, we are looking the answer to this question is 4. So when we want to implement this 2-input exclusive NOR gate by using only minimum number of 2-input NOR gates, the answer is 4. If you try this for exclusive OR operation, for exclusive OR gate, using minimum number of 2-input NOR gates, we want exclusive OR operation. It is possible for us to speak now. For complementation purpose, we need one more gate. This gate output we want to read as Y complement. It means we want to have this AX NOR B complement. So effectively we want to read it is exclusive OR between A and B. For this purpose, the 5th NOR gate what we are using, it is inverter and the input will be Y. Hence we are having here exclusive NOR operation. So what we are looking exclusive OR operation. So what we are looking is, for XNOR implementation, we are having the usage of 4 gates. For XOR implementation, we are having the usage of the 5 gates. And of course, both we are implementing with NOR gates. And of course, minimum number of 2 input NOR gates. The minimum number of 2 input NOR gates. So when we are trying to implement the XNOR with the minimum number of 2 input NOR gates, the answer is 4. When we are trying to implement XOR with the minimum number of 2 input NOR gates, the answer is 5. So we are having here, based on this, as we said, the 9 gates, NOR gates are functionally complete or universal logic gates. We are having possibility to implement any digital circuit in general, or any Boolean function, or any digital system in general. We are having possibility to implement just by using only 9 gates, or just by using only NOR gates. It is a reason to speak the 9 gates and NOR gates as universal logic gates. And corresponding operators, of course, we are naming as functionally complete set operators. Now, what are the things we discussed till now? Let us consolidate. With the minimum number of 2 input the minimum number of 2 input 90 gates, they are trying to implement all these logic gates. Of course, we are taking here all these gates except not, of course, remaining, we are talking as 2 input gates. So the consolidated information possible to speak now. For NOT operation 1 gate, for AND operation 2, for OR operation 3 gates, for NIND operation, of course, 9 with 9, no means. But I mentioned this, the reason we can see later. For NOR operation, we know, for NOR operation we are in need of 4 gates. It is there on the board. For NOR operation, we need 4. For exclusive OR operation also we need 4, but exclusive NOR operation we need 5. As similar to this with other universal logic gate, that is NOR gate, we need to try. With a minimum number of 2 input NOR gates, if we look the implementation of these gates. For NOT operation, of course, here also 1. For OR operation, we need 2. For AND operation, we need 3. For AND operation, we need 3. And for NIND operation, we need 4. That is the reason I mentioned here. For NIND operation, we need 4. And for NOR, with an NOR, of course, no need to talk. It is only 1, in fact. XOR operation, we need 5. It is the one what we are looking. XOR operation, we need NOR gates 5. And XNOR operation, we need 4. So it is a consolidated thing, and we need to remember this data. As I said already, you will be having few standard questions without any work. Just remembering these numerical values, you need to speak the answer, particularly about this exclusive OR and exclusive NOR. Exclusive OR with the minimum number of 2 input NOR gates 5. With the minimum number of 2 input NAND gates 4. Similarly, exclusive NOR with the minimum number of NOR, it is 4. The number of 9 it is 5. So generally you will be having questions on these. These are the very regular, very frequent questions. No need to talk which year, when it was. Most of the competitive examinations will be having the questions in the defense lab or ISRO or GATE exam or engineering service, etc. Let us continue with this universal gates topic only, little more for a few more questions. F1 is AB, F2 ABC, F3 ABCDE, F4 A B complement C, F5 A complement B, C, D complement E. Let's look here now. For implementation of these products, all these are basically we are looking as a product terms. For implementation of these products, if at all we are looking with the minimum number of 2 input NAND gates, with minimum number of 2 input NAND gates, if we try. For implementation of AND operation between A and B, the implementation of the AND operation between A and B, we are looking, the answer is 2. Similarly, the implementation of AND operation between A, B, C, if you speak, it is possible to read the answer based on our previous knowledge. If you look, for implementation of AB, we need 2. If I name it is X, X and C needs 2. So that for implementation of A, B, A and with B and with C needs 4 gates. And similarly for the implementation of A, B, C, D, E, it is possible to look here. For AB implementation 2 gates, for CD implementation 2 gates. If I name it is X1, if I name it is X2, for this purpose 2, and finally X and with E needs 2. So while counting 1, 2, 3, 4, while counting, we are looking to the answer as 8. While looking to these numerical values, just think, is it possible to make any formula type of approach? Just think, can we make any formula type of approach on this question? We are having possibility while looking to these answers, possibility for a formula approach. The formula what possible to speak is, it is 2n minus 2. This is a formula we can speak. This is a formula possible to speak. Where n is number of literals in the product, number of literals in the product. Number of literals in the product. If you look here, n is 2. Here n is 3, here n is 4. So substituting these values, and if you check the numericals what we mentioned, they are coming as the answers. When n is 2, 2 into 2, 4, 4 minus 2, 2. When n is 3, 3 into 2, 6, 6 minus 2, 4. When n is 4, 2 into 4, 8 minus, sorry. A, B, C, D, E. Sorry, this n is 5, not 4. Wrongly I mentioned. So when n is 5, 2 into 5, 10, 10 minus 2, 8, and so on. So like this, it is possible to make the answer. So based on this, suppose I am having a product something F6. This F6 consider as A, B, C, D, E, F, G suppose. I am having here n. If you count here, n is 7. N is 7. Check well. If any numerical mistake is there, tell me. Rectify yourself. N is 7. 1, 2, 3, 4, 5, 6, 7. So based on this, look into the formula. Possible to speak 2n, that is 14. N is 7, so 2n is 14. 14 minus 2. So answer is 12. Answer must be 12. So like this, we can speak with a formula based. Similarly, let us come to this F4. In the case of this F4, number of literals are 3. Using this formula, if you try 2 into 3, 6, 6 minus 2, 4. But here we are having B complement. So getting complement, for complement purpose, we need one gate. Complement purpose, we need one gate. Hence, answer to this question is 5. Using the formula, using this formula 4, and because of this complement operation, we need plus 1. Hence, answer is 5. You can check your notes, or you can rewind your video and you can see one of the previous questions we are having as same. The minimum number of 2 input NAND gates required to realize f of A, B complement C. It was the question. It was the question in the 98 gate gate EC paper. We already discussed. You can rewind the video and you can see there. Anyway, answer is 5. Based on this, the F5, we are trying to look to the answer. F5 is concerned, the number of literals are 5. So using this formula, 5 into 2, 10. 10 minus 2. 10 minus 2 is 8. But we are having complement operation on 2 variables. 2 literals, basically we are looking with a complement. Because of this, we are looking here plus 2. Plus 2. Hence, answer to this question is, or to this product answer is 10. By using this formula, it is 8. Because of this complement operation, for each one on each variable, for complement purpose, we need one 90 gates separately as an inverter. So the total number of gates we need as 10. So like this, it is possible to identify. So whenever we are having a product something like this with maybe any number of variables, we can speak the answer by using this formula. If you are remembering this formula well, with a shortcut, whenever we are having any question of this nature or any of this nature, without much time spending, possible to speak the answer with less time. So it's a shortcut to speak the answers question. Be clear, just single product we are talking here. Once we are having the work, the implementation by using 90 gates, we should not stop our work, our thinking only with the 90 gate, because we are having a sister as a universal gate, that is NOR gate. A 90 is a brother and NOR is a sister. So we need to try. We tried with the brother, and of course we should not leave there. We need to try even with the sister. So we need to try even with the NOR gates. So if you take the question with the minimum number of 2 input NOR gates, for implementing of AB, for implementing of AND, sorry, for implementation of this AND operation, we know here it is a circuit what we are looking at the board, it is not removed. So we need 3 gates. And for implementation of this A and B and C, if you look, as similar to the previous case of 9, we have to look for AB purpose, we need 3 gates. If I name X, AB, and result is X, X and C needs 3. So 3 plus 3, we need here 6 gates. We need here 6 gates. Similarly, if the product is on 5 variables A, B, C, D, and E, for AB purpose, 3 gates. For CD purpose, 3 gates. And while naming it is X1, it is X2. For reading this X, it is X1, and with X2, we need here 3 gates. Finally, X AND with E needs 3 gates. So if you count the number of gates, we are looking 1, 2, 3, 4. So that the number of NOR gates we need as 12. Number of NOR gates we need as 12. While looking to these numericals on these samples, try to think about the formula. If anything is possible, try to think about that formula. The answer is supposed to be as a formula possible to make. The formula possible to make here is 3n minus 3. The formula possible to speak as here 3n minus 3. For the first case, n is 2. So 3n 6 minus 3. So 3. For F2 case, n is 3. So 3n is 9. 9 minus 3 6. For F3, n is 5. 3n is 15. 15 minus 3 12, and so on. So based on this, suppose if you look to this F6, F6 is concerned n is 7. So 3n is 21 minus 3. So answer is 18. For F6 purpose, we need 18 gates. Because n is 7, 3n 21 minus 3, so 18. And similarly, let's work out for F4, F5. In this F4 and F5, we are looking one of the variable or few of the variables in general I am talking, or with complements. In other cases, what we look till now, F1, F2, F3, and F6, the variables are without complement, but other 2 examples what we are looking at the board, F3, F4, they are with few literals are with few variables are with complements. So in this case, if you think, what must be the answer for this? What's supposed to be the answer for this F4? A, B complement C. For implementing of A, B complement C using minimum number of 2 input NOR gates, what's supposed to be the answer? If you try well, the answer to this question must be 5. The answer to this question must be 5. Let me check how it is so. A, B complement we are having. So F4 is A, B complement and with C. For getting A, B complement, let us try how many gates we need. For reading AB, 2 input NOR gates were need of 3. For reading AB complement, we are in need of only two gates. Only two gates. You can check how it is so. When we are having here AB, when we are having here AB, on the variable A and on the variable B, we are performing complement operation before feeding to this third gate. If we want to have the complement operation on the B, if we want to have the complement operation on the B, then if you don't want complement, then it is to be complemented before feeding to the last gate. If you want complement, you can understand there is no need of any such NOR gate. We must feed directly B here. If you are feeding B directly to this gate, we are looking here, one input is A complement and other input is B. So A complement R with B, by using De Morgan's property, it is AB complement. It is AB complement. So what we are looking, if we don't want complement, then we are having the usage of NOR gate. If we want complement, simple way you have to understand, simple way you have to make a correlation to our thought process. If you don't want complement, NOR gate is required. If you want complement, remove the NOR gate, that's all. Remove the NOR gate, that's the way you have to remember. So you have to make a correlation, not any by-hearting required. It is a thought process you have to give the concepts what we are learning, not with any by-hearting. By-hearting won't help to perform well in any GATE exam. If your learning is concept learning, then only you'll be having a better performance in any exam, wherever you go. The by-hearting, with the numerical, with the formula, with the everywhere shortcut, if at all you're bothering, that won't help you to do best. Maybe required shortcuts to manage the time, but everywhere you can't try. So conceptually you have to think, we are having our thought process conceptually. Shortcuts, all these things are the part of these concepts only. Anyway, the answer is 2 for implementation of AB complement. So what we are looking here, the formula what we can look here is same 3n minus 3. So 3n minus 3, n is 3, 3n is 3n. So n is 3, 3 into 3, 9, 9 minus 3, 6, minus 1, minus 1. Because of the complement on one variable, it is minus 1. It is minus 1. Because we are looking here, if you want clearly the circuit, for clarity I am putting, but to avoid this. This is your A. This is your B. So we already identified it is resulting AB complement. Now AB complement and with C we want. AB complement if I name X, later what we need? X and with C. So X and C definitely needs 3 gates. So what we need here? So this is X complement, this is a C complement, while naming to C. So coming to this will be X complement or C complement, whole complement. It is X and with C, where X is AB complement, and of course and with C. So total gates, if you count, the total gates are 5. Total gates are 5. We are having subtracting of the gate while reading AB complement. So in general, whenever we are having a complement, it is subtraction with implementation with the NOR gates. But the same thing we were looking earlier with the 90 gates, it is addition. It is addition. The products when we are implementing with the 90 gates, when we are having complement, it's addition. But when we are having the usage of the NOR gates, it's a subtraction. It is a subtraction. So based on this, for F5, if you look, N is 5. So when N is 5, we are looking 5 into 3, 15. 15 minus 3, 12. 12 minus, it is 12 minus, on two variables we are having complement minus 2. Hence, the answer to this question must be 10. Answer to this question must be 10. So we are looking, N is 5. Because of 5, 5 into 3, 15 minus 3 is 12. We are having complement operation on two literals, so subtraction of 2 we need. When the complement is on one literal, subtraction of 1. Complement is on two variables, subtraction of 2. Complement is on three variables, subtraction of 3. Hence the answer is 10. So like this, we can make the formula. So conclusion is, whenever we are having implementation of these product terms, single product terms with the 90 gates, without any complement, it is only 2n minus 2. Whenever we are having complement, 2n minus 2 plus some k. K is number of variables which are with complements. And when we are having implementation of the NOR gates, the formula is 3n minus 3 without any complement on the variable. As and when we are having complements, the formula is 3n minus 3 minus k, where k is number of variables which are with complements, where k is the number of variables which are with complements. Like this, we need to remember. So when we tried this sort of work with the product terms, definitely we need to try this sort of work even with the sum terms, So all this work we are trying to look just by using the universal logic gates. So F1 let us name A or B, F2 let us name A or B or C, F3 let us name A or B or C or D or E, F5 let us name A or B complement, F6 let us name A or B or C complement or with D. F7 let us name A complement B, C complement D or E complement. Some terms I mentioned here. This we are trying to implement now with the NOR gates and 90 gates, of course, with only 2 input case. 2 input NOR gates minimum. How many we need to try. Similarly, later we'll be trying minimum how many 2 input 90 gates required. For F1 purpose, A or B, for A or B operation, we know from this work what we had. We need 2 gates. For F2, A or B or C, so definitely we can speak for A or B we need 2 gates. If I name it is X, X or C needs 2 gates. So total we are speaking we need 4 gates. Similarly for F3, if you read, for A or B we need 2 NOR gates, for CRD 2 NOR gates, while naming it is X1, it is X2, this needs 2. So XRE needs 2. So total number of gates, if you count, we are need of 8. 2 plus 2, 4 plus 2, 6 plus 2, 8. So based on this formula, definitely you can make a correlate the work what we are having earlier with the 90 gates. The formula what we are using here is 2n minus 2. The formula what we are using is 2n minus 2, where n is number of variables, number of literals, where n is number of literals. N is number of literals in some term. In some term. Earlier it was product term, now it is sum term. Number of literals in sum term. So if you look here, n is for the first case 2. So 2 into 2, 4 minus 2, 2. For second case, n is 3. So 3 into 2, 6 minus 2, 4. For F3 case, n is 5. So 5 into 2, 10. 10 minus 2, 8, and so on. So based on this, suppose if you speak some function as F8, F8 consider which is A or B or C or D or E or F or G. Suppose it is 1. So we are looking here n value here as 7. Is it? 1, 2, 3, 4, 5, 6, 7. So whenever n is 7, definitely we are talking the answer to this question is 12. N is 7, 2n, 14. 14 minus 2, the answer is 12. Okay. So whenever we are having a sum term, assuming no variable is having a complement, then the sum term may be consisting of any number of variables. Just using this formula 2n minus 2, we are having possibility to speak the answer. Now let us come to the case, suppose F5 variable, one of the variable is complement, A or B complement. In that case, your guess supposed to be, the answer to this question supposed to be 3. The reason is, for A or B complement purpose, we need A or B complement purpose, we need 2 gates, assuming B bar is available. But truly speaking, B bar is not available. To get the B bar, we need 1 more gate. So total number of gates are coming to be 3. So A or B bar, so multiple ways you can think. When I am having A or B bar, A or with X, let us name, where X is B complement. So for A or X, so it is similar to the F1, so we need 2. But because of this complement, I need 1. So total number of gates we need 3. Hence, you can speak the same formula. If you look here, n is 2. So 2 and 2, 2n minus 2. So 2 into 2, 4 minus 2, 2. And because of this complement operation, we are having plus 1. We are having plus 1. So the answer is 3. So similarly, if you look to the F6, n is here 5. So 2n minus 2, 2n, that is 10, 10 minus 2, 8. 8 plus, because of the complement, 1. So, because the complement 1, so that answer is 9. N is 5. So 2n is 10, 10 minus 2, 8. Sorry, n is, here not 5, very sorry, it is 4. So if any such numerical is mistake we are having, just to make a correction. Possible extent, it may not be the case, if at all anything. N is 4. So 4 into 2. 4 into 2 is 8. 8 minus 2, 6. So 6 plus 1. It is 7. Answer is 7. So as I said, multiple ways you can think the answers. ARB needs 2. C bar RD needs 2. C bar as is I am talking later, I will take complement. Later among these two sum terms or operation need 2. So 6. Because of this complement 1. So that's 7. Total we need 7. Similarly, for F7 we are having, not earlier, here we are having N is 5. So because of this 5 into 2, it is 10. 10 minus 2, 8. So this is 8 having complement on 2 variables. Having complement on 2 variables, it will be plus 2. Hence, answer is 10. Answer is 10. So the conclusion is, if at all we are having in the sum term any variable with a complement, for each complement we need a separate NOR gate. For each variable we need a separate NOR gate. We are having complement on 2 variables, then we need 2 gates. We are having complement on a single variable, we need 1. I think here complement I mentioned even on this, so that it will be 3, not 2. So 3 variables. So if it is not having complement, plus 2, having A also complement, if at all you are looking 3, so 8 plus 3, it is 11. Okay. It is not 10, it is 11. We missed earlier with A also having complement because of this plus 3. So if you try this, as usual, with its brother, that is with the 90 gates, we need to try. So without much time spending, with the knowledge of earlier work on the products, possible to speak little fast. When we are taking a question with a minimum number of 2 input, (90 gates). The minimum number of 2 input 90 gates, if you see, for ARB operation, we know here we need 3 gates. We need 3 gates, ARB operation. It's the one what is mentioned there. So we need here 3 gates. For A or B or C, definitely we are talking the answer is 6. Because for ARB operation we need 3. If I name it is X, ARB result let us name as X. X or C needs 3. So 3 plus 3, 6. And based on this, F3 will be here 3, here 3. To make a R here we need 3. Finally to make R here we need 3. So 3 we are looking here 4 times 3 into 4, 12 gates. So formula, if at all we are talking here, our answer for formula will be 3n minus 3. N is 2 for the first case F1, 3 into 2, 6, 6 minus 3, 3. For second case F2, N is 3, so 3 into 3, 9, 9 minus 3, 6. For F3 case, N is 5, so 3 into 5, 15, 15 minus 3, 12, and so on in general. So based on this F8, if at all we are looking, the answer to the F8, because of N is 7, 3 into 7, 21, minus 3, answer is 18. So 3 into 7, 8, 21, 20 minus 21 minus 3, it is 18. So similarly, let us try for F5, F6 and F7 there, where here F5, F6, F7 we are looking complement operation. So you can make a correlation here. Instead of addition, it's supposed to be subtraction, because it is an observation what we are having while working with the NOR gates on the products. NOR gates and the products. Here we are working with the 90 gates on the sum terms. So it is correlation. So subtraction operation will be having. If you look to the previous table, that is the identification what we are having. So if you look here, for clarity, let us speak F5 clearly. A or B complement. So A or B complement. A or B complement by using 90 gates. If you look here, if you want the variable without complement, then before sending the variable to the last 90 gate, it is to be complemented. It is to be complemented. If we want the complement operation here, then the variable we supposed to send directly to the last gate. If we are sending the variable directly to the last gate, it is A complement and with B whole complement. By using De Morgan's property, the result is A or B complement. So that we are not in need of this 90 gate. So here the formula, if you want to use, it is to be subtraction formula. It is to be subtraction formula. So here, if you look here, formula is concerned n is 2. So 3 into 2, 6. 6 minus 3. 6 minus 3 will be 3 minus 1 minus 1, because of the complement and the variable B. So it is 2. It is observation what we are having there. It is observation what we are looking there clearly. So based on this, F6 will be n is 4. N is 4 means 3 into 4, 12 minus 3. 12 minus 3 is 9, minus, because of 1 complement, subtraction of minus 1. So once subtraction of minus 1, the answer is 8. Verify once again. N is 4. So 3 into 4. 3 4 is 12. 12 minus 3, 9. Because of the complement operation, subtraction minus 1. So answer is 8. Similarly, coming to this, in the F7, n is 5. So 3 into 5, it is 15. Minus 3, 12. 12 minus, we are having complement operation on 3 variables. Because of 3 variables, we are having complement minus 3 operation. So 12 minus 3, the answer is 9. So like this, we can read. Hence, whenever we are having any question, with single sum term, with a single sum term, not multiple sum terms, with a single sum terms. Whenever we are having any question with single terms like sum terms like this, if the variables are not having complement, when we are having implementation of the NOR gate, simple formula 2n minus 2. The variables are not having complement, the simple formula for 90 gates, 3n minus 3. Of course, 2 input case. Minimum number of 2 input case we are talking, both the cases. As and when we are having the sum term, few of the variables are complements. If one variable is complement, with the NOR implementation, addition of 1. With the 9 implementation, subtraction of the 1. 2 variables are complement in the sum term. With the NOR implementation, 2 will be addition. With the 9 implementation, 2 will be subtraction. So how many number of variables are complemented? With the NOR implementation, it is addition. With the 9 implementation, it is a subtraction. So you have to remember like this easily. So thing is, when we are talking about the product terms, products are very closely related with the 9s. When we are talking the sum terms are closely related with the NOR. So when they are closely related, the formulas will be same, 2n minus 2. When we are having 9 with the, when we are having implementation of the product with the 9, closely related, we said 9 and product term, so 2n minus 2. And when we are talking about some terms and NOR gates are closely related. So formula here also 2n minus 2. And when the products are implemented NOR, they are not closely related. In that case, the formula is 3n minus 3. When we are having some implementation of the 9 some terms are not closely related. So formula is 3n minus 3. When we are talking without any complements. The complement, of course, we said when it is closely related plus, when it is not closely related, when it is loosely related, it is a minus. On the number of, if at all n number of, if at all k number of variables are having subtraction, if they are all closely related, addition. If they are not closely related, it is loosely related, then it is a subtraction. Like this, we need to remember. Little practice it demands. So to remember this, so by hearting is not advisable. You need to practice a little. So what is said here as a table, just try to watch more than once if at all it is required, and work out yourself with paper and pen. Hopefully, without any difficulty, you can remember. Few questions. Let's take a question. The minimum number of 2 input NAND gates required. The minimum number of 2 input NAND gates required to realize the Boolean function A complement or BC. The minimum number of 2 input NAND gates required to realize the Boolean function f. So, if you look properly, without any sort of paperwork, you supposed to speak the answer as a 2. When we are talking about shortcut, with your all the knowledge and the concepts, you're supposed to speak the answer is 2. If you look how it is so, I can read this A and with BC complement whole complement by using De Morgan's property, that is the 12th property. We can speak this is A and with the BC whole complement. So once there is a case, so anything is required to think. For BC complement, you need 1 NAND. Later, the BC complement, if you say X, effectively it is A X whole complement, you need 1. So 1 plus 1, the answer is 2. So like this, you must frame the idea, you must speak the answer. So that is a shortcut. So you have to remember the concepts. With the concepts, you can speak the answer fast. Let us come to the next question. Note down. When the given circuit is implemented, using minimum number of 2 input NAND gates, the number of NAND gates required, dash a bit. When it is implemented with 2 input NOR gates, minimum number of NOR gates required. When it is implemented with the minimum number of 2 input NOR gates, then the minimum number of 2 input NOR gates required, dash. Suppose It is a question. It was a question in 2005 GATE CS paper itself. It was a question. 15 years back, it was a question in the GATE paper. So to identify the answer to this, let us read first what is the function we are having implementation by the given logic circuit. The function which is implemented by the given logic circuit is here, I think I supposed to write here XYZ. Sorry. Because they are taking the variables as XYZ. So f of XYZ. When we are having this notation, it is a default means it is the most significant bit variable. This is the least significant bit variable. After f, what is the variable we are having? The first variable, it is a MSB variable, and so on. Z is the LSB variable. It is a default means always. If you look here, the NAND gate output is X and with Y complement, whole complement. This AND gate output, of course, YZ. So this gate output we are reading as X and with Y complement and with YZ whole complement. So one input is X, Y complement, whole complement, other input is YZ. Hence, X, Y complement and with YZ. When we are having this sort of expression, better you have to evaluate first innermost. So innermost, if you evaluate, this is giving X complement or Y and with YZ. So this is X complement Y or with Y, X complement YZ or with YZ whole complement. So YZ, while taking as a common within the parenthesis, it is X bar or with 1. So this is resulting. This is giving a result F as YZ complement, because we know by using third property what we listed under the Boolean algebra properties heading, it is 1. So 1 and with anything, one of the property again, it is second property. So YZ whole complement. Once we are having the YZ whole complement, when we are having this question, implementing this function, what is the function which is implemented by this logic circuit when you want to implement by using only 2 input NAND gates, definitely the answer to this question is only 1. Direct answer we are looking, the answer to this question is 1. And when we are having this with the minimum number of 2 input NOR gates, with the minimum number of 2 input NOR gates, we look based on our previous work. You can rewind the video and you can see I listed also a table for NAND implementation with NOR operation. It is as good as speaking the NAND operation between YZ. The NAND implementation with the NOR gate, definitely the answer is 4. Because the NOR gates AND operation needs 3 gates. Just I am revising what we mentioned. For AND operation we need 3 gates. For NOR operation we need, AND operation we need 3 NOR gates. For NAND operation we need plus 1. So 4 gates. In fact, it is there in your notes. You can see, you can rewind and you can check in your video also, or if at all you made it notes, you can check the notes. The answer is 4. Okay. Note down. Identify whether the given Boolean function is a self-dual function. Identify whether the given Boolean function is a self-dual function. Identify whether the given function is a self-dual function is a question. In our earlier discussion, we know already how to write the dual operation for a Boolean function or Boolean equation or Boolean expression. In the dual operation, what we are looking is we are having interchanging of these operators and we are having interchanging of these Boolean constants. When we are writing the dual for a given Boolean function or equation or expression, the changes what we are looking is the or and AND operators are interchanged and the Boolean constants 0 and 1 are interchanged. Here we are having a new term. That new term what we are looking is self-dual. So try to understand or try to speak what's supposed to be the meaning of the self-dual. What's supposed to be the meaning of the self-dual? What's supposed to be your guess on the word self-dual? The meaning of the self-dual is for the given function f, consider fd is a dual function. For the given function f, assume fd is a dual function. Fd is a dual function. If fd is equal to f, then we are speaking the function f is a self-dual function. Then we are speaking the function f is a self-dual function. So better make a note. Consider fd is the dual of the function f. Consider fd is the dual of the function f. If fd is equal to f, then the function f is said to be self-dual function. Let us back to the question. The function is given in the compact canonical SOP form. On this function, we are having a question whether the given function is a self-dual function or not. Identify whether the given Boolean function is a self-dual function or not. So given function, default is a Boolean function only. We are dealing with the Boolean algebra. So whether I am mentioning or not mentioning, default it is referring to only Boolean functions, not any other normal functions. So to identify whether the given Boolean function is self-dual function or not, for this compact canonical SOP form, let us write first expanded canonical SOP form. The expanded canonical SOP form of this function is minterm 1 product form x complement y complement z. So these things you must be in a position to read directly. Whenever I am having x, y, z values as 0, 0, 1, it is referring to the minterm 1. As a product, it will be x complement y complement z. When I'm having 2, definitely you must write as x complement y z complement. So such a practice is expected. So no need to write all these things. Without writing this sort of things, you must be in a position to write. It will come with a practice, in fact. Similarly, the minterm 4 will be x, y complement, z complement. The last product will be x, y, z because we are having, it is 7. So 7 means 1, 1, 1. Definitely this will be x, y, z. So as I said, for your clarity here, I may be writing, but if at all you are bothering to spend less time on such questions, shortcut way, if you at all are bothering to cut down the time, so you have to avoid all this work that you can do with the practice. Now we can try for the real operation on this function. If we try the real operation on this function, it must be fd of xyz. It must be fd of xyz. So fd of xyz will be x complement, y complement, or z, and with x complement or y or z complement, and with x or y complement or z complement, and with x or y or z. It is a dual of the function f. Now we are looking, this expression is in the expanded canonical POS form. The expression what we are reading is in the expanded canonical POS form. Once we are looking in the expanded canonical POS form, we can look the max terms. Possible to read the max terms. This is the max term 6. So I am having here some term as x complement or y complement z, means here x is 0, y is 0. Sorry. Here x is 1, y is 1, z is 0. Then we are having the sum term as x complement or y complement z, that is referring to the decimal 6. Similarly, this is referring to the decimal 5. The reason is same. Here x must be 1, z must be 1, y must be 0. So it is referring to decimal 5. So based on this, this will be 3, this will be 0. So the max terms for this real function 0, 3, 5, 6. These are the max terms. The function is on 3 variables. On 3 variables, total number of combinations are possible. Total number of combinations are possible 8. Out of 8 possible combinations, we are looking 4 combinations are the max terms. So the leftover 4 combinations, definitely they must be min terms. So here our question is whether fd is equal to f or not is a question we need to check. We are having the given function f with the min terms. The function what we developed as a real function, we are looking here the max terms. So from this work, you have to check. So from this work, if you want to check, you can't conclude at this stage or at this stage. At this stage, while looking, coming to this, you can't make a one-to-one relation, so you can't make any conclusion whether it is equal or not. While reading this, we are looking to this max terms. While knowing these max terms, we are talking the leftover combinations of the min terms. The leftover combination we are reading as 1, 2, 4, 7. In fact, the given function is having the same combinations as the min terms. Hence, the fd is equal to f. Once fd is equal to f, the given Boolean function is a self-real function. The answer for this is yes, the given Boolean function is a self-real function. It is answer to this question. It was a question, the 2001 GATE paper. It was a question. So this function was given and it was a question whether it is self-real function or not to check. It was a question. Now, while looking to this discussion, you have to look little more on this self-real functions. We need to understand little more on these self-real functions. The understanding what we need on these self-real functions is understanding what is expected is, when a function is possible to be self-real function with a shortcut, can we speak? That is one thing you need to know. While looking to this given function, maybe in this compact canonical form, can we able to speak? Is it a self-real function? The shortcut. When a function is possible to be self-real function, we need to understand. When a function is possible to be a self-real function, then we can speak this. And we need to talk. We need to understand. Suppose we are having function on n variables. By using n Boolean variables, how many number of self-real functions are possible? How many number of self-real functions are possible? How many number of self-real functions are possible? These things we need to identify. So for this understanding, let us work some theory part. So what I am mentioning is, the shortcut, can we recognize given function is self-real function or not? When we are naming a function as self-real function, we are trying to understand. And by using n Boolean variables, maximum how many number of self-real functions are possible, we'll try to identify, we'll try to speak. So to understand this, let's start the work like this. Let us take the case of the three variables. The variables let us consider as x, y, and z. When we are having these three variables, for this minterm 0, assume it is a minterm, then the product will be x complement, y complement, z complement. It is x complement, y complement, z complement. On each one of the literal, if you take the complement operation, then it will be x, y, z. Correspondingly, for this product, the equivalent decimal number is 7. Correspondingly, for this product, equivalent decimal number is 7. This pair we are naming as mutual exclusive pair. This pair we are naming as mutual exclusive pair. Mutual exclusive terms, in other way, mutual exclusive terms are mutual exclusive pair. Similarly, the product form for minterm 1 will be x complement, y complement, z. While taking complement on each literal, it must be x, y, z complement. So equivalent decimal value for this product term is 6. So this 1 and 6 also we supposed to say, this 1 and 6 also we supposed to speak as mutual exclusive pair. Basically, they are the mutual exclusive pairs on the variables x, y, z. They are the mutual exclusive pair on all the three variables. They are the mutual exclusive pair on variables x, y, and z. They are the mutual exclusive pair on the variables x, y, and z. Is it? Similarly, if you write the product form for 2, it must be x complement, y, z complement. While taking the complement on each literal, the product is x, y complement, z. The equivalent decimal value is 5. Hence, this 2 and 5 also the mutual exclusive pair on the variables x, y, z. They are the mutual exclusive terms on the variables x, y, and z. Similarly, if I write the product form for 3, the product form for 3 is x bar, y, z. On each one of the literal, if you take the complement, it must be x, y complement, z complement. So this is decimal 4. So 3 and 4 also mutual exclusive pair on variables x, y, z. They are the mutual exclusive terms on the variables x, y, and z. So on 3 Boolean variables, on these 3 Boolean variables, we took as the variables x, y, z. We are having, these are the 4 mutual exclusive pairs. These are the 4 mutual exclusive pairs. The pairs what we are looking is, one pair is 0, 7, 1, 6, 2, 5, and 3, 4. These are the 4 mutual exclusive pairs. This function f what we discuss, this function f what we discuss, it is a self-dual function. It is a self-dual function. Now let us take the question. Let us name the previous function is f1. Let us take, say, f2. f2 is, say, on xyz with the min terms, say, for example, as 0, 1, 4. If you want to make a check whether it is a self-dual function, while looking to this, your answer supposed to be this is not a self-dual function. Why it is not a self-dual function? If you speak, if you write here, we are having the 3 products. Products will be x comp. For clarity, I am writing. No need of writing all this work basically, but for making more clear, more clarity, I am putting here. It is a 1. After this, when you write the dual operation on this, we are having here 3 sum terms. We are looking here sum terms, 3 sum terms. So when we are having 3 sum terms, we are having the max terms only 3. Max terms are only 3. So based on this, the min terms will be left over. We'll be having 5 min terms. We'll be having 5 min terms. But the given function is having only 3 combinations as the min terms. If that is a scenario, is it required to do all this work? If that is the case, is it required to do all this work? Definitely, the answer is no. No need to do all this work. No need to do all this work. Okay. So you can avoid all this work without doing any sort of work. You can speak. This is not a self-dual function. From this, we are understanding if a function is to be a self-dual function, on this 3 variable case, we need to have 4 combinations, exactly 4 combinations must be min terms in the given function. Whenever in the given function exactly 4 combinations are the min terms, then only we are having a possibility. We are not saying it is. We are not speaking it is a self-dual. We are not talking that. We are having a possibility at that time. The function may be self-dual function as and when the given function is having 4 combinations as the min terms on the 3 variable case. On the 3 variable case, 4 combinations of the min terms means half of the combinations are the min terms. On 3 variable case, total number of combinations are 8. Out of 8 combinations, as and when 4 combinations the min terms, then there may be possibility the given function may be as a self-dual function, but it is not guaranteed to be always. We'll see why it is not guaranteed to be always. But as and when we are looking, 4 combinations are not the min terms, something like this, 3 combinations or 6 combinations or 2 combinations or 7 combinations like this, what all we are having. Default you can discard without any sort of work. Shortcut, you can speak. definitely that is not resulting to be a self-dual function. A function is to be self-dual function means half of the combinations must be minterms. So from this we will be having a conclusion. I will speak that conclusion later. So conclusion, the understanding what we are having till now, what is the work we did. So if you want to speak any function on n variables is to be self-dual function, first of all the basic check is half of the combinations must be minterms. It means remaining half of the combinations must be maxterms, or equivalently the number of minterms are equal to the number of maxterms. That I will speak as a statement later. Hence this f2 is not a self-dual function. So what are the point we identified? When a function is possible to be self-dual, what are the point we identified based on this? Whenever we are having half of the number of combinations, then it is possible maybe self-dual. One of the point we identified, the question what we took. Next, consider the function as f3. Here f3 of xyz, consider the minterms for this function as 0, 1, 2, 7. 0, 1, 2 and 7 are the minterms. 0, 1, 2 and 7 are the minterms. Again our question is to check whether it is a self-dual function or not. So primary check we are doing, function is on 3 variables and we are having out of 8 combinations of 3 variables, so 4 combinations of minterms. Once the 4 combinations of minterms, it may be, we are not talking it may be possible to be a self-dual function. That is not a final decision, final conclusion is not. It may be possible because half of the combinations we are reading as the minterms. And if we see further, whether it is self-dual function or not, as similar to the f1, let us try to verify as a beginning question. So as similar to f1, if you check here, you have to look quickly the product form for each one of these minterm, x complement, y complement, z complement for 0 and x complement, y complement, z for 1, and for 2 it is x complement, y, z complement, and for 7 it is x, y, z. For easy adapt, I took here this 1 to 7 what we are looking earlier in the f1, those only I mentioned. So for easy quick work, only accept this. Anyway, it's a way to write. Now we are looking the dual operation, or we are writing the dual for this function f3. Then it is x complement, y complement or z complement, and with x complement or y complement or z, and with x complement or y or with z complement. So I mentioned some time back, don't name it is plus, name as or. Okay, it's the best way to speak. I already mentioned some time back. So this next term will be x or y or z. So f3 of d, what we are looking, it is in the pivoist form. Basically expanded canonical pivoist form, because every sum term contains all the variables. Of course, variable may be complementary or uncomplimentary form. Now if you look to the equivalent decimal value for each sum term, this is 7, it is 6, it is 5. The story is same. Here it is 5. The reason is x is 1, z is 1, y is 0. So 5. Y is 0. So 5. And so on other things. And this will be 0. Hence, we are having here the max terms 0, 5, 6 and 7. Once these 4 combinations are the max terms for the dual function, out of 8 combinations, 4 combinations the max terms, so remaining 4 combinations must be min terms. So leftover combinations are the min terms. The leftover combinations are 1, 2, 3 and 5. These are the leftover combinations. And if you check now this function with the f3, this is not equal to F3 because the min terms are differ. The min terms are differ, so that is not equal to F3. So what we are looking is the function F3 finally conclusion is it is not a self-real function. Finally, we are having a conclusion F3 is not a self-real function. So as similar to the F2, we are unable to eliminate at the first instant itself. The reason is we are having here half of the number of combinations of three variables, half of the number of combinations of the three variables are the min terms. Because of this, we had a further work. Based on this further work, we are looking at conclusion the F3 is not a self-real function. So that as and when we are looking, the number of min terms in the given function are equal to half of the number of total number of combinations, half of the number of total number of combinations as and when we are looking, that function may not be guaranteed to be always self-real. But a function is to be self-real, that condition is followed. That condition is to be followed. If a function is to be self-real, half of the number of combinations are to be min terms. But whenever a function is having half of the number of combinations as the min terms, there is no guarantee all such functions are self-real functions. So let's try for one more example. So let's try one more example this side. Let's take the question as F5, the same variables x, y, z. So let's look here the min terms as zero, 2, 4, 6, 0, 2, 4, 6, 0, 2, 4 and 6 are the min terms. Now again we are taking a question whether this function is a self-real function or not is the question for us. So primary check, we are looking on these three Boolean variables. We are looking in the given function 4 combinations of the min terms. On the given Boolean function, because of 3 variables, total 8 combinations. Out of 8 combinations, half of the combinations are min terms. Then there is a possibility, because this condition what we mentioned is coming to be true. So there may be a possibility the function F5 may be self-real function. So to conclude whether it is self-real function or not, we have to make a check as what we did for F1 and F3. So if you make a check, for that purpose, you have to read first for this function the expanded canonical. For this function, we must read first expanded canonical SOP form. The expanded canonical SOP form is x complement, y complement, z complement, r with x complement, y, z complement, r with x, y complement, z complement, r with x, y, z complement. Now let us write the dual operation on this function. When we write the dual operation on this function, f5 of d of x, y, z is equal to x complement r with y complement r with z complement and with x complement r y r z complement and with x or y complement r z complement and with x or y or z complement. So after writing the dual operation, the expression what we are looking, the expression is in the expanded canonical POS form. The expression we are reading in the expanded canonical POS form. Because of the expanded canonical POS form, we are reading the max terms. Of course, each sum term we can recognize, we are recognizing as a max term. So this is the max term is 7. It is the max term 5. It is the max term 3. It is the max term 1. So we are having the function with the max terms of 1, 3, 5, 7. These are the max terms to the function f5 of d. It is basically the dual function for the given function f5. So the leftover combinations are 0, 2, 4 and 6. These are the leftover combinations. Function is as usual on the 3 variables. So 4 combinations the max terms, the remaining 4 combinations must be min terms. The remaining 4 combinations we are reading as a min term, they are 0, 2, 4, 6. And we are looking, the given function is having the same combinations as the min terms. Once the given function is having the same combinations of min terms, then we are having a conclusion f5d is equal to f5. So dual of the function f5 we are having as f5. Hence, the function f5 is a self-dual function. The function f5 is a self-dual function. So now, while looking to these examples, the final conclusion we can talk on the self-dual functions. The conclusion what we can speak on the self-dual functions is, if a function is to be a self-dual function, first of all, it must be a neutral function. The meaning of the neutral function is the number of min terms must be equal to the number of max terms. The meaning of the neutral function is number of min terms must be equal to the number of max terms. So it is a necessary condition to check a function is to be a self-dual function. Okay, we'll make a statement later, but the things what we learned I mentioned. Now we'll look further based on the examples what we discuss. We are having here the function f1, the function f5, of course I can name maybe f4 better, f3 I can name as a f4. Okay, we are looking here the function f1 and f4 are self-dual functions, and anyway f2 no need to talk, f3 is not a self-dual function. So with this understanding, let us see what is happening, the work what we are having earlier before coming to these examples, before coming to particularly the examples f2 to f4. In the f1 function, the min terms, if you see, min terms are 1, 2, 4, 7. 1, 2, 4 and 7. These are the min terms. In the f1 function. And in the f3 function, min terms are 0, 1, 2, 7. 0, 1, 2 and 7. These are the min terms in the f3. And similarly, in the f4 function, the min terms are 0, 2, 4, 6. 0, 2, 4 and 6. 0, 6, 2 and 4. These are the min terms. So we are having a conclusion, f1 is self-dual function, f4 is a self-dual function, whereas this f3 is not a self-dual function. Looking to this, we are able to speak. In this f3 function, a complete mutual exclusive pair is present. Complete mutual exclusive pair is present. So this complete pair is min terms in the f3. But in the case of the f1 and f4, we are not having a scenario like this. We are not having a situation like this. Complete pair is not used as the min terms. Complete pair is not used in the f1 case or f3 case as the min terms. Whereas in the f3 case, complete pair is used as a min term. So conclusion is, a function is to be a self-dual function. First of all, it must be a neutral function, and later we are looking a function is to be self-dual function if and only no mutual exclusive pair present as the min terms. No mutual exclusive terms must present as the min terms in the function. Whenever we are not having mutual exclusive pair or mutual exclusive terms as the min terms in the function, then we are having the function is a self-real function. So these are the conclusions what we are having while looking to the work what we are having with these examples. Hence, we are looking to the consolidated information. The consolidated information we need to talk as like this. So better make a note. Better make a note. A function we want to look when it is self-real function. So first condition we are talking. If a function is to be self-real function, then the function must be neutral function. Then function must be neutral function. Function must be neutral function. The meaning of the neutral function is number of minterms must be equal to the number of maxims in the function. Number of minterms must be equal to the number of maxims in the function. So this is nothing but, conclusion is, this is nothing but, if at all the function we are talking on n Boolean variables, if we are having a function, then this will be to the power of n by 2 number of minterms, or to the power of n by 2 number of maxims. Of course, to the power of n by 2 we can read as to the power of n minus 1. As and when we are having a function something like this, it is to the power, it is not following the rule of the to the power of n by 2. When the situation is not the case of the to the power of n by 2, then definitely the function is not at all possible to be self-real function. So as and when we want to check a function is to be self-real function, first we are making a identification whether in the given function we are having the number of minterms are equal to the number of maxims, or equivalently we are talking a new term, whether a function is a neutral function or not, we are checking. The meaning of the neutral function is this. Then the second condition is no mutual exclusive terms in the function. No mutual exclusive terms. No mutual exclusive terms in the function. No mutual exclusive terms in the function. If these two conditions satisfies, it is necessary, it is sufficient. If these two conditions are satisfied, then only the function is possible to be a self-real function. Then only the function is possible to be self-real function. It's a conclusion. So to check whether mutual exclusive terms present or not, assuming in the first scan this condition satisfied, that is function, the given function consider is a neutral function. Something example what we are having here, this f2 is f3, something what we are looking here, it is f3. So what we are looking is, it is a neutral function because number of minterms are equal to the number of maxims. But coming to the second condition, it is fail. So second condition is no mutual exclusive terms present. We are talking, if at all mutual exclusive terms are present, then the function is not a neutral function. Not a self-real function. We are having here a mutual exclusive pair with the detail work we are looking 0, 7. It is a mutual exclusive pair, mutual exclusive terms. So this pair is present. Because of this, it is not a self-real function. And our work is with a shortcut how to recognize, not going into such a detail. To understand, we did all the detail work, but with a shortcut, if at all we want to look, whenever in the given function, while adding the decimal values corresponding to the minterms, when we are adding the decimal values, if it is equal to 7, then it is indication a mutual exclusive pair is present corresponding to those decimal numbers. In that case, that function is not a self-real function. In that case, the function is not a self-real function. Say for example, 0 plus 7, while adding this, it is 7. So whenever we are looking sum of these two decimal numbers and three variables I am talking is equal to 7, then correspondingly the mutual exclusive pair is present. That is, a 0, 7 is a mutual exclusive pair. You can see from the work what we are looking here. So that function is not a self-real function. So based on this, suppose if I talking other functions, say f, I think we took up to f4, so f5, let me name f5. If I am having the min terms, say for example 1, 2, 4 and 6, suppose, whether it is a self-real function or not, if at all it is a question. If you take this as whether it is a self-real function or not, it is happened to be the first condition satisfied. It is a neutral function. The number of min terms are equal to half of the number of the total number of combinations, or number of min terms are equal to the number of maxims, or half of the number of total number of combinations. Total number of combinations are 8 by 2, 4. So first condition is satisfied, then we are looking further to check the second condition. Second condition, what I said, no mutual exclusive pair should not present. You can see here 1, 6 ready work is there. You can see there. Here 1, 6 is a pair. So we are looking here while making correlation here. 1, 6 is here. So while knowing that, we are talking this. So mutual exclusive pair is present. Hence, the function f5 is not a self-real function. But I am talking little alternatively with the shortcut. The shortcut is whenever we are adding the decimal values corresponding to the min terms, if the decimal, while adding those decimal numbers, only two decimal numbers, while adding two decimal numbers, corresponding to min terms, corresponding to min terms in the function, default in the function, while adding any two decimal numbers corresponding to the min terms, of the function, if it results 7, on 3 variable case I am talking, if results 7, then that function is not a self-real function. We are looking here 1 plus 6, result is 7. So it is not a self-real function. But it is not the case with the f1. It is not the case with f4. While adding any two decimal numbers corresponding to the min terms of function, we are not having the result as 7 here. Or similarly, you can check with the f4. Here also, while adding any two decimal numbers, we are not having the result as 7. But in the case of this f5 or in the case of this f3, while adding two decimal numbers corresponding to the min terms of function, we are having the result is 7. Hence, these functions are not self-real functions. So it is a shortcut way to identify whether a function is a self-real function or not once the function is a neutral function. The function is not neutral function, we are not coming to this. We are coming to this check when the function is a neutral function. The first check is whether it is a neutral function or not. Once it is a neutral function, we are looking with the shortcut. The next step is while adding any two decimal numbers which are corresponding to the min terms of the function, whether it is equal to 7 or not. On 3 variable we are talking. Once it is equal to 7, we are talking the function is not a self-real function. So this is a discussion we are looking on the 3 variables. So on n variables, if at all we are talking, then definitely on n variable, our check supposed to be to the power of n minus 1. So here n is 3, to the power of 3 minus 1, 7. In general, for n variable case, for 2 variable, 4 variable, 5 variable case, the check supposed to be while adding two decimal numbers which are the minterms of function, if the result is not resulting to be, it should not result adding two decimal numbers. If it is coming to be 7, the function is not a self-real. It is not a self-real. And if you want to be self-real, then it should not be equal to 7, or it should not be equal to the power of n minus 1. So while adding any two decimal values corresponding to the minterms of the function, if the result is not coming to be equal to in general to the power of n minus 1, then only the function is self-real. If it is equal to the power of n minus 1, then the function is not a self-real function. So these are the observations from the work what we are having here. So looking to the work lengthy, but now with all this knowledge, when this question is given, how to identify the function, if you see the identification we are doing based on this work. Suppose I am putting a question something as like this. The given functions S1, S2, S3 and say S4. From the given function, which one of the function is self-real function, if at all it is a question. So while looking to this, we are quickly recognizing it is not a self-real function because it is not a neutral function. First condition fails. Coming to this, they are the neutral function. Coming to this, it's a neutral function. Now we are checking while adding two decimal numbers because the function is on three variables, whether sum is equal to 7 or not. We are checking. While adding here, sum is 7. So we are concluding it is not a self-real. While adding this, sum is 7. So it is not neutral. So like this we are checking. So it is a shortcut way to identify whether a given function is a self-real function or not. So we completed this work. So when a function is possible to be self-real, how to identify the function is to be self-real. The next point what we mentioned is maximum how many number of self-real functions are possible using n Boolean variables is a question. So while looking to all this work, it is possible now to speak. It is possible to speak. If a function is to be self-real function, on three variable case we are talking, among this pair, we are taking any one combination of the minterm. So possibilities are 2. Similarly, from this pair, any one we are using as a minterm. From this pair, any one combination we are using as a minterm. From this pair, any one of the combination we are using as a minterm. So possibilities from each pair, 2 possibilities we are having. From each pair we are having 2 possibilities. So from this we are talking total how many number of functions are possible. If you speak, it is 16. It is 16. From each pair we need to take only one combination of the minterm, then only we are having a possibility the function is a self-real function. If you take any pair completely, then definitely that function is not a self-real function. That is the identification, that is the discussion what we did till now. On 3 variable case, we are looking maximum number of self-real functions are possible are 16. If you take the question on n number of Boolean variables, it is the one which is interested as mentioned in the beginning of the discussion. So on n Boolean variables, if you do the pairing like this, so the pairing will be ij, kl, like this. If you think total how many pairs we are having, if you take as a question, the total number of pairs will be to the power of n by 2. N is 3, total number of pairs are 4, to the power of 3 by 2. So 4. If at all the general case on n variables, the last pair, this will be to the power of n by 2th pair. So this is to the power of n by 2th pair, n by 2th pair. So we are looking here from each pair any one combination. So we are having a multiplication of these two like this. If you look, how many times it is multiplied? It is multiplied based on this to the power of n minus 1 number of times it is multiplied. To the power of n by 2 is nothing but to the power of n minus of 1. So 2 is multiplied to the power of n minus 1 number of times. Hence, the answer is to the power of n minus 1. By using n Boolean variables, we are taking a statement as by using n Boolean variables, maximum number of self-real functions are possible. Maximum number of self-real functions are possible. Maximum number of self-real functions are possible. The answer to this is to the power of n minus 1. It is the answer to this question. So this is most of the times it is a direct question in the GATE paper. It was a question many times. Recent times, I think 2014, it was a question in the GATE paper. So many times it is a question in the GATE exam, in CS paper, EC paper, EE papers, many papers. A standard question it is. So by using n Boolean variables, maximum how many number of self-real functions are possible? If you take as a question, the answer is to the power of n minus 1. Now looking to all this discussion, so this is maximum number of self-real functions, how many possible on n Boolean variables. If at all we are taking a question on n Boolean variables, maximum how many neutral functions are possible? How many neutral functions are possible? How many neutral functions are possible if you take this as a question? So on n Boolean variables, total number of combinations are to the power of n. And what we need, a function is to be neutral function, then the number of min-terms, a function is to be neutral function, number of min-terms must be to the power of n by 2. So to the power of n minus 1 number of combinations must be min-terms. So how many possibilities we are having if you look? So answer to this question, maximum number of neutral function maximum possible. So maximum how many neutral functions are possible? If you are coming to the answer to this question, maximum number of neutral functions possible. If you come to this question, definitely our answer is to the power of n, c to the power of n minus 1. The answer will be maximum how many neutral functions, maximum number of neutral functions, how many possible? That is the question what we took. The answer to this question is to the power of n, c to the power of n minus 1. So based on this, the self-real functions, number of self-real functions are subset of the number of neutral functions. It is subset of number of neutral functions. With the numerical values, let us check. On n Boolean variables, we are talking number of neutral functions, maximum number of neutral functions. Of course, maximum. We are targeting to the maximum. Number of neutral functions, maximum, how many possible? And similarly, number of self-dual functions. Number of self-dual functions, of course, for maximum. So formula for neutral functions is this to the power of n c to the power of n minus 1. For self-dual functions, it is to the power of n minus 1. So let us check. Suppose n is 3. Suppose n is 3. We are looking, this is to the power of 3 c to the power of 3 minus 1. So to the power of 3, 8. C to the power of 3 minus 1 means 4. So if you check well, 8c4, hopefully it result as 70. Let me check. So 8c4 means 8 into 7 into 6 into 5 divided by 4 into 3 into 2 into 1. Of course, this, let me cut this. So we are looking, it is 70. It is 70. Whereas the number of neutral functions we look, self-dual functions we look, it is coming to be to the power of 3 minus 1, effectively to the power of 2. So 16. It is 16. Say, it is a two variable case. The two variable case, we are looking here, this is to the power of 2c to the power of 2 minus 1 means to the power of 1. So 4c2. 4c2 is 4 into 3 divided by 2. So that 6. It is 6. And self-dual functions will look to the power of 2 minus 1 means to the power of 2 only. Hence 4. It is 4. So what we are looking, the number of self-dual functions are coming to be subset of number of neutral functions. Number of self-dual functions are coming to be subset of number of neutral functions. So you can see here now as it is neutral functions. So self-dual functions will be subset. Self-dual functions will be subset. These are the conclusions what we are looking. So like this you can try maybe for any other case n value, and maybe 4, 5, etc. So conclusion is every neutral function may not be a self-dual function, but every self-dual function is a neutral function. To check a given Boolean function, most of the time our concern is on the self-dual function. To check whether the given Boolean function is self-dual function or not, first check is whether it is a neutral function. The condition fails, then we are not bothering anything. That function guarantee is not a self-dual function. If the first check, the condition is coming to be true, it is a neutral function if at all, then we are looking to second condition. Second condition is we are adding to any two decimal numbers and we are looking to the decimal value. The decimal value, as long as not equal to this to the power of n minus 1, then no problem, the function is self-dual function. But as and when it is equal to the power of n minus 1, then the function is not a self-dual function. Like this we are having a conclusion. So it is a work which is expected. Hopefully you understood what we discussed, all these concepts. That textbooks may not speak all these, but of course, this sort of questions we are having. So to handle this sort of questions, it is a knowledge which is expected. If you are unable to understand the first watching of the video, better rewind and watch one more time. Hopefully, without any difficulty, you can understand. If still any problem, you can post a question in the Medici portal, respective portal. So on your own, you try this question. After some time, I will discuss this question. Whether the given Boolean question is, how many functions are possible? Question is, how many functions are possible so that f of xyz is equal to f of x comma y complement comma z. How many functions are possible? How many functions are possible so that how many functions are possible so that f of xyz is equal to f of x comma y complement z is a question. Suppose if I am giving some options like this, so try to identify the answer. So with proper reasoning, you try yourself. After some time, probably in the next video, I will discuss the solution to this question. Okay, at this point, we'll stop.